Okay, so we're going to take some notes here and pick up where we left off in class yesterday. I apologize, I'm still feeling under the weather, so if you hear me sniffling, sorry about that. Also, I have a dog somewhere around the house. I don't know if he'll make noise, and currently Minions is on in the background, so I apologize. But let's go ahead and get to this. So we've been solving trigonometric equations, and we have several more examples left, and then we have some practice problems that we'll go through as well. So solving this one here, the thing that we notice is that we have sine squared, sine, and cosine squared. So we've got two different functions, okay? And we don't have a GCF that would allow us to factor and do zero product property. These two terms have a GCF, but as far as all four terms, because there's 1, 2, 3, and 4 terms, there is no GCF. So what we're going to have to do is use our Pythagorean identity and rewrite this so it is just one trig function. Now, the fact that we have a sine squared and a sine means we're going to want to change the cosine squared into a sine squared, okay, using the Pythagorean identity, excuse me. So let's go ahead and remember that sine squared of x plus cosine squared of x is equal to 1. So for us, the identity that we could use is that cosine squared of x is equal to 1 minus sine squared of x. So we'll take this, we'll replace it with 1 minus sine squared of x, bring down our equal sign, and the left side will bring down sine squared of x minus sine x plus 1. Now, we'll zoom in here a little bit. Excuse me. Let's get everything to one side. And again, if it helps you to think of it, again, you could always think of this as being s squared minus s plus 1 equals 1 minus s squared, and solve it that way, all right? So let's go ahead and subtract the 1 and add sine squared x to both sides. So subtract 1, add sine squared x to both sides. Kind of mark our middle side here. So equals, on the right-hand side, everything's going to cancel out, leaving us with 0, which was the intent. Anytime we're dealing with quadratic equations, we want to have it set equal to 0, so we could either use a quadratic formula or factor. So on the left side of the equation here, we get 2 sine squared of x minus sine of x. Sorry, I forgot the x there. And then the 1's cancel out. So we just have 2 sine squared x minus sine x equals 0. In terms of solving this, I do have a GCF for both of these, and that GCF is equal to sine of x. So I could factor that out, and we get sine of x times 2 sine of x minus 1, and that's equal to 0. Now we can apply zero product property because I have this times this, and it's equal to 0. The only way to multiply and get 0 for an answer is if you multiply by a 0. So either the sine of x has to equal 0, or 2 sine of x minus 1 has to equal 0. Okay? Now, in terms of solving these, sine of x equals 0, we do inverse sine of both sides, and that will cancel out, and we get x equals the inverse sine of 0. Now, we discussed this in class. We're not just finding the inverse sine of 0. We're solving an equation. We're trying to figure out when the sine of x equals 0, and that contains multiple possibilities. Now, in this problem, it did mention specifically that we want any answer on the interval from 0 to 2 pi. So we're going to ignore our normal idea that inverse sine can only be quadrants 1 and 4, and we're going to look at all possibilities between 0 and 2 pi. So when we look at 0 to 2 pi, trying to figure out when the inverse sine of 0, that's a quadrantal angle. So if I look at my 4 quadrantal angles, we have 1, 0, 0, 1, negative 1, 0, and 0, negative 1. So when is the sine going to be equal to 0? Well, sine is the y value, so that happens at here and here, the positive and negative x-axis. So this first half of the equation gives us the answers x equal to 0, or, excuse me, not or, but and x equals pi. Now, let's consider the other possibility. The other possibility, we had 2 times the sine of x minus 1 equals 0. So if we start solving this one here, we get 2 sine of x is equal to 1. Divide each side by 2, and we get sine of x is equal to 1/2. So again, we're looking for any answers in the region from 0 to 2 pi. Well, sine is positive in the first quadrant and again in the second quadrant. So here's my right angles. Sine is opposite over hypotenuse, so 1 over 2, 1 over 2. Now we just got to figure out what reference angle that is. Well, turns out that reference angle would be 30 degrees, or pi over 6. And same here, pi over 6. Now my actual angle, though, is measured from 0. So to here, we get x equals pi over 6. And then to this one here, we would get x equal to 5 pi over 6. So ultimately, if we look at all the answers that we got here, we got x equal to 0, x equal to pi, x equal to pi over 6, and x equal to 5 pi over 6. So let's write our answer down. X equals 0, pi, pi over 6, and 5 pi over 6. Okay, let's try the next one. Okay, so they want us to find all the solutions for the equation 3 cosine of 2x equals e to the x plus 1 on the interval from 0 to 2 pi. And I'm going to be honest, we kind of don't have any techniques to solve this. We have 2 completely different functions. What we see here is a cosine function and an exponential function, okay? We can't rewrite one as the other, so the only way we're going to be able to do this is use a calculator, all right? So on our calculator, we are going to type in y equals 3 times the cosine of 2x, and then we're also going to type in y equals e to the x plus 1. All right, now the key here is setting our window to see what we need to see. So our x values, we have an interval that goes from 0 to 2 pi. That is going to be our x values. So our x min is going to be 0, and our x max is going to be 2 pi. Now, to come up with our range for the y values, or our range, I guess, let's consider what this function right here looks like, okay? We have a vertical shift of 0, and we have an amplitude of 3. So normally, cosine of x bounces between a maximum of 1 and a minimum of negative 1. This one is going to now bounce between a maximum of 3 and a minimum of negative 3. Okay, so our y min will be equal to negative 3, and our y max will be equal to positive 3. Now, as far as the scale is concerned for these, you could just leave the scale at whatever it's set to. It doesn't make a difference, okay? So now let's go ahead and type this into our calculator, set our window, and take a look at what it looks like. Okay, to the best of my abilities here, I'm going to try and draw what my calculator screen is showing, and it looks kind of like this. Now remember, we set our x values to go from 0 to 2 pi, and our y values to go from negative 3 up to a maximum of 3. So we see our x-axis going right down the middle of the graph, okay? And our cosine function, we will see, starts up here in the upper corner, and it ends up here in the upper corner. It's going to reach the top again in the middle, and then it gets the bottom right about here, and it's the bottom right about here. Okay, and to the best of my abilities, I'm going to try to make that a nice smooth curve. And oh my goodness, am I just amazing with my artistic skills. Said no one ever. Okay, then we have our e to the x function. Okay, I'll do that one in red. And our e to the x function just kind of peeks out in that upper corner of the graph. So by visual inspection, there is only one point of intersection. So to calculate that, on our calculator, we are going to do second and trace, which brings up the calculate menu. And then we are going to calculate number 5, which is an intersect. And if we do that, we will get an intersection point according to our calculator. I can read this, it's really tiny. X equal to 0.326 and y equals 2.385. Now, in this equation, the only variable we have is the x variable. So we're solving for the x, so we're going to list the x value, not the y. And over the interval from 0 to 2 pi, we just have the one answer. So the only answer to this equation is x equals 0.326. And there, that's that one. Okay, taking a look at this next example, we have two different functions, sine and cosine. However, there is no identity that will turn sine into cosine or cosine into sine, except for the cofunction identities, which doesn't apply because they both have x as the angle. The closest thing we have is a Pythagorean identity, but in order for that, we need things to be squared. So we are going to square this function. However, when we have two different trig functions, before we square it, we want to make sure that we have one trig function on one side of the equation and a trig function on the other side of the equation, okay? We don't want to have two on the same side, because if I were to square both sides right now, this right side would just turn into 1, but this left side would give me a sine squared of x, and then it would give me minus 2 sine x cosine x, and then plus cosine squared of x. So it gives me that term that has both a sine and a cosine in the middle, which is going to be too difficult for us to deal with. So instead, if we get sines on one side and cosine on the other side, and it doesn't matter where that extra 1 term goes, so we'll just add, sorry, let me erase this squaring here. And I apologize if you're getting motion sickness for some reason. This thing just kind of moves around a lot. Apologies there. Okay, so if we add cosine of x to both sides, we get the equation sine of x equals cosine of x plus 1. Now, if we square both sides, my left side is just going to turn into sine squared of x. My right side will turn into cosine squared of x plus 2 cosine of x plus 1. And that just comes from doing cosine of x plus 1 times cosine of x plus 1 and a little distributive property. Okay. Now, like one of the earlier problems, I can take a Pythagorean identity for sine squared of x, because sine squared of x is 1 minus cosine squared of x. And if I substitute that out for 1 minus cosine squared of x equals cosine squared of x plus 2 cosine of x plus 1. Now I have an entire equation where everything is in terms of cosine of x. So I'm going to go ahead and get one side equal to 0. So I'm going to subtract 1 and add cosine squared of x. And the result of that will be 0 on the left side. On the right side, we get 2 cosine squared of x plus 2 cosine of x, and then the 1's cancel out. So what we have here is quadratic, but because there is no c term at the end, this is really easy to factor by GCF. And if I factor by GCF, we get 0 equal to 2 cosine of x times cosine of x plus 1. And now we can use zero product property, split this apart, and we're going to get 2 cosine of x has to equal 0, or cosine of x plus 1 has to equal 0. Okay, both of these are going to be quadrantal angles. If I divide both sides by 2 here, we get cosine of x equal to 0. And if I think about my coordinate plane, here's my quadrantals. We get 1, 0, 0, 1, negative 1, 0, 0, negative 1. Cosine refers to the x value, so cosine is going to be 0 up at the top and at the bottom. So here we get x equal to pi over 2 and 3 pi over 2. And then on the other side, we subtract 1 from each side, and we get that the cosine of x has to equal negative 1. Well, that is also a quadrantal angle. So if I think about my 4 points, 1, 0, 0, 1, negative 1, 0, 0, negative 1, cosine is equal to negative 1 right there. So that gives us the answer x equals pi. So if I'm going to write down all my answers on the interval from 0 to 2 pi, I am going to have to include x equal to pi over 2, 3 pi over 2, and pi. Okay, the next several problems are just duplicate examples of the ones that we've done. So these would be good ones for you to try on your own and then come back and watch to see how we did them, okay? So I'll pause right now if you want to pause the video, try this on your own. This is just like the very first example we did, okay? All right, so assuming you've taken the time to do this problem, let's see how this one works out. We only have one trig function in this problem, that is sine of x. So we're going to treat this as if it's a simple equation. Again, if it helps you, think of it as being just s plus root 2 equals negative s. We're going to bring the variables to one side, put the root 2 on the other side, okay? So what would that look like? Well, we're going to get plus sine of x plus sine of x, and then we get 2 sine of x plus root 2 equals 0. Then we're going to subtract root 2 from each side, and we get 2 sine of x equals negative root 2. Then we're going to divide each side by 2, and we get sine of x equals negative root 2 over 2. Okay, so we're trying to figure out when x is going to be equal to negative root 2 over 2. So x equals inverse sine of negative root 2 over 2. Well, let's picture our coordinate plane here. Here's our coordinate plane. Sine is going to be negative in the 4th quadrant and again in the 3rd quadrant. So let's make our right angles here. Now, as far as having a ratio of root 2 over 2, hopefully we recognize that comes from 45, 45, 90. So that means this angle here is going to be pi over 4, pi over 4. Okay, so measuring from 0, the first answer we get would be x equals 5 pi over 4. The second answer we get, measuring from 0, would be x equals 7 pi over 4. Now, this equation, if we look back, did not give us any restrictions on solutions. It didn't say just from 0 to 2 pi, so that means we have to consider all possible solutions. Since sine has a period of 2 pi, what we have to do is we have to add multiples of 2 pi to each answer. So that's going to give us x equals 5 pi over 4 plus 2 pi n, or x equals 7 pi over 4 plus 2 pi n. All right. Okay, so this is just like our second example that we had. We just have a tangent function. It is squared, so we're going to need to take the square root at some point. So let's go ahead and start solving. We add 15 to both sides. We get 5 times the tangent squared of x equals 15. Divide each side by 5. And we get tangent squared of x equals 3. Okay? Then we take the square root of each side. And we get that the tangent of x equals plus or minus square root of 3. Again, we're not just asking the square root of 3, we're asking what squared equals 3, so that means we have to consider both the positive and negative. So now, tangent x has a period of 0 to pi. So we're going to look at 0 to pi. Our ratio can be positive or negative, so that means we are going to be in quadrant 1 and quadrant 2. Okay? In quadrant 1, to get a tangent ratio of root 3, that means this side would have to be root 3, this side would have to be 1. Okay? So that is going to match up here with pi over 3 on both sides. So our actual angle is going to go from 0 to here. So we get x equals pi over 3, or x equals, to this one, would be 2 pi over 3. Now again, tangent has a period that goes from 0 to pi, or period of pi, I should say. That means we have to add intervals of pi. So ultimately, to show all solutions, because it doesn't restrict us on where we can answer, our first answer would be pi over 3 plus pi times n. And our second answer would be 2 pi over 3 plus pi times n. And that covers all possible answers. All right, so obviously this one falls along with our third example. We're going to have to use factoring here. However, if we look carefully, this is not a standard quadratic. This is something that fits quadratic form. So when I go to factor this, I've got to be careful that it's not going to factor into a tangent times a tangent. We are starting with tangent to the fourth, and then we have tangent squared in the middle. So when I factor this, it's going to be two things. One of them is going to be 2 times the tangent squared of x. Got to leave more room there, sorry. And the other one is just going to be tangent squared of x, because it's tangent squared of x times tangent squared of x that will make tangent to the fourth of x. So now we just have to figure out what numbers will go here that will work to give us the correct term in the middle. And that is going to be a plus 5 here and a minus 3 here. I could check that because 2 tangent squared of x times negative 3 is going to give me a negative 6. And then 5 times tangent squared is going to give me a positive 5. Negative 6 and positive 5 will combine to make negative 1 in the middle. So go back, and this is equal to 0. Now we can apply our zero product property. Again, we've got something times something, and it's equal to 0. The only way that happens is if we multiply with the 0. So either 2 times the tangent squared of x plus 5 has to equal 0, or the tangent squared of x minus 3 has to equal 0. Okay, so let's take a look at the left side here. If we start solving this, we'll subtract 5 from each side, and we get 2 times the tangent squared of x equals negative 5. Divide each side by 2. Tangent squared of x equals negative 5 halves. take the square root of each side, and then we get tangent. That is a really, does not look like the word tangent, apologies. We get tangent of x equals, well, no solution because can't take the square root of a negative number. Wah, wah. All right. On the other side, however, we'll add 3 to both sides of the equation, and we get tangent squared of x equals 3. Then we'll take the square root of each side, and we get that the tangent of x equals plus or minus the square root of 3. And again, tangent of x has a period of pi, so we're going to make our coordinate plane here. Since my ratio can be positive or negative, I could be in the first quadrant or the second quadrant. This side would be root 3, this side would be 1, this would be root 3, this would be negative 1. The angle that makes that work is pi over 3, pi over 3. So measuring from 0, we get one answer of pi over 3. And then we get another answer of 2 pi over 3. Now, double check. They did want us just to use the interval from 0 to pi, so we're good. We don't have to add any extra triangles here. So that's our answers. X equals pi over 3, or x equals 2 pi over 3. Okay, got another word problem here again. So again, they're telling us all the information that we need. So our initial velocity is 36 meters per second, and it's got to clear a barricade 70 meters away. So we're going to plug in our values, and we get the equation 70 equals 36 squared times the sine of 2 theta divided by 9.8. Now we just have to start solving. So we're going to multiply both sides times 9.8. Okay, that's going to give us 686 on that side and 36 squared sine of 2 theta. All right, now we're just going to divide each side by 36 squared. Divide by 36 squared. You can figure out what 36 squared is first, but since we're just doing it all on calculator, doesn't really matter. And we get sine of 2 theta on this side. And now on the other side, we get 0.529. Okay, so now we got to take the inverse sine of that. Okay, so we're going to do inverse sine of 0.529 and inverse sine of 2 theta. The right side, they just cancel out and we get 2 theta. The left side, if I do inverse sine, and if you kept this answer, or the answer to this question here, 686 divided by 36 squared, if you kept that on your calculator, don't type in inverse sine of 0.529, type in inverse sine of the answer, okay? That'll give you more exact. Okay, now this is a word problem, so you're going to want to make sure that your calculator is in degree mode. I know it's frustrating having to switch back and forth from problem to problem, but we want to make sure we're doing, you know, the appropriate calculation here, as accurate as we can. All right. And we get an answer of 31.96 degrees. Oops, wrong utensil. 31.96 degrees. Now, if we think about the situation in this problem, we're talking about shooting a golf ball over a barricade, okay? So just visually speaking, here's the ground, here's a golf ball, here's a barricade, ball's going over the barricade. Now, obviously, if I shoot the golf ball at too small of an angle, it won't go over the top of the barricade. So we got to have a minimum angle. Likewise, if I shoot the golf ball at too steep of an angle, it's going to fall way short. It'll go high enough to clear it, but it won't make far enough to clear it. So that means we have to have two different angles. We have to have a lower end and an upper end. Well, sine is positive in the first quadrant, but sine is also positive in the second quadrant, which means right now, this angle that I have, and no, I haven't solved for theta yet, but we were trying to figure out when sine was going to be equal to 0.529. Again, that could happen here or here. So the calculator told us, it's not a reference angle, so that we had to use a calculator. The calculator told us that, we would get 31.96 degrees. Okay, well, to figure out this angle here, again, 31.96, if I just do 180 minus 31.96, we get 148.04. Okay, so now we'll realize that this is the value of 2 theta. So we get 31.96 equals 2 theta, or 148.04 equals 2 theta. And to solve this, we're going to divide each side by 2. And here we end up with theta being equal to 15.98, and theta equal to 74.02 degrees. So that means I need to be at least 15.98 degrees, but no more than 74.02 degrees. So we want to hit the ball at an angle between 15.98 degrees and 74.02 degrees. Okay, this one again is like example 5 this time. We have different functions. We have sine and cosine, okay? But the sine function is squared, so I could use a Pythagorean identity and get this entire equation in terms of cosines, which will make my life easier. So our identity is that sine squared of x equals 1 minus cosine squared of x, okay? So that's going to give us, with that substitution, 2 times 1 minus cosine squared of x equals cosine of x plus 1. Little distributive property on the left side here, we get 2 minus 2 cosine squared of x equals cosine of x plus 1. Now, I see that it's quadratic in nature, and solving quadratic equations is easier when our quadratic term is positive. So I'm actually going to move everything over to the right side of this equation. So I'm going to subtract 2 and add 2 cosine squared of x. Subtract 2 and add 2 cosine squared of x. Left side, everything cancels out to be 0, which is what we need for quadratic. And on the right side, we have 2 cosine squared of x plus cosine of x. They're not like terms, so I can't put them together, excuse me. And then positive 1 and negative 2 gives me minus 1. So now, if we factor, we get 2 cosine of x and cosine of x. And then to get the negative 1 and the positive 1 in the middle, we're going to do minus 1 and plus 1. Okay, and that will give us all the correct terms. So now we could apply zero product property, and we could say that 2 cosine of x minus 1 equals 0, and cosine of x plus 1 equals 0. If I solve this one on the left side here, we add 1 to both sides. 2 cosine of x equals 1. Divide everything by 2, and we get that the cosine of x equals 1/2. And if I picture my coordinate plane, okay, now before I forget, I do want to point out here that this did give us the interval 0 to 2 pi. Okay, so we're looking at any possible answers around this whole thing. So knowing that cosine of x has to equal positive 1/2, we could be in the first quadrant or the fourth quadrant. Cosine of 1/2 would be 1 here and a 2 here. And if I think about my reference triangles, that would make this angle right here pi over 3. So measuring from 0, we get x equal to pi over 3, or x equal to, and that would be 5 pi over 3. Now, the other half of the equation, or the other half of zero product property, I should say, gave us cosine of x plus 1 equals 0. If we subtract 1 from each side, we get the equation cosine of x equals -1. That's a quadrantal angle. So if we think about our 4 quadrantal angles here, we have 1, 0, 0, 1, -1, 0, 0, -1. Now, all those are a possibility because, again, we're looking anywhere from 0 to 2 pi. Well, the only one that gives us a cosine equal -1 is that one right there, which is just pi. So this equation here gives us the answer x equal to pi. So ultimately, I have 3 possible answers. X equals pi over 3, x equals 5 pi over 3, or x equals pi. Not a fan of this program. It keeps moving things around, sorry. Okay. All right, so like exam 5, we got to solve this. Here's the problem. We have, again, a mix of functions. We have a trig function, cosine x, but then we just have plain old variables, okay? They do not mix. They are not in the same world. So what we're going to do is we're going to bring the plain variables to one side, and so we get x squared minus x equals 2 cosine of x. All right, and now we're going to use our calculator. We want to make sure that our mode is in radians. Okay, anytime we are using trig functions and other types of functions, we have to be in radians. Okay, because otherwise in degrees, x would be degrees for everything, and degrees doesn't make sense in other functions. Degrees only make sense in trig functions. Whereas radians doesn't have units, okay? So radians is just a plain number. That makes sense in any function. So we'll make sure our calculator is in radian mode. And we are given the interval 0 to 2 pi, so our x values is going to go from 0 to 2 pi. Again, we don't have to worry about the scale. Our y values, we need to think about what's happening with our cosine side, okay? So cosine of x, again, normally goes from a high point of 1 to a low point of -1. We have an amplitude of 2, though, so that's going to stretch it from +2 down to -2. So we're going to set our y min at -2 and our y max at +2. And now we're going to type y equals x squared minus x for one function, and y equals 2 cosine x for the other function. And let's take a look and see what we get on our calculator. Okay, so let's see how neatly I could draw this here. So again, on our calculator, here's our little screen. Again, we're going from 0 to 2 pi on the x-axis, and -2 to +2 on the y-axis. Our x-axis runs down the middle here. Okay, now our cosine function, we'll do in blue, starts up in this corner here, and then in the middle of the graph, it comes down to the bottom, and then it ends back up at the top there. So looks kind of like that. Not bad. All right, and then our other function, x squared minus x, excuse me, I'll do that one in red. That looks like this. Okay, now that leaves us just this one point of intersection. So if we do second and trace, that brings up the calculate menu. And we're going to calculate an intersection point. Sorry for the delay. And we get an intersection point of x equaling 1.341 and y equaling 0.456. Well, again, the only variable that's in our actual equation here is x's. So I just need to know the x value. So my answer is x equals 1.341. Okay, last example here. So in this one where we have two different functions, sine and cosine, but we don't have any squared functions. So, and we don't have any GCFs that we might be able to factor anything. So what we're going to do is we're going to square both sides of this function. The only thing that we want to make sure of is that we have one of each function on each side, okay? In which we do. We have cosine on the left and sine on the right. So we're going to start by taking the left side and squaring it, and taking the right side and squaring it. Now on the left side, if I square that, and again, I'm just doing 1 plus cosine of x times 1 plus cosine of x, use distributive property. It's not a difference of squares, so you're going to get more than just a 1 and a cosine squared of x. So if I distribute this all out, my left side is going to be 1 plus 2 cosine of x plus cosine squared of x. And on the right side, if I square that, I'm going to get 3 sine squared of x. Okay, now I have a cosine squared and a sine squared, which will allow me to use a Pythagorean identity. In terms of which one I'm going to use, since I have cosine and cosine squared x, but for sines I just have a sine squared x, I'm going to want to replace this with the Pythagorean identity, so that way everything will be in terms of cosine. So the identity that I could use, again, is that sine squared of x is 1 minus cosine squared of x. All right, so zoom in here. This is going to give me this equation. 1 plus 2 cosine of x plus cosine squared of x equals 3 times 1 minus cosine squared of x. Little distributive property over here. 1 plus 2 cosine of x plus cosine squared, if I could write cosine squared of x, equals 3 minus 3 cosine squared of x. Again, when we're solving quadratics, it's most helpful if our quadratic is a positive term. So we're going to add 3 cosine squared of x to both sides, and we have to subtract 3 from both sides. That's going to give us the left side, the right side is 0. On the left side here, we get negative 2 plus 2 cosine of x plus 4 cosine squared of x. I'm going to rearrange this and put it in standard form. So 4 cosine squared of x plus 2 cosine of x minus 2 equals 0. I do have a GCF of 2 over here. So I could just, since it's a constant, I could just go ahead and divide each side of the equation by 2. Now I can't do that if I had a variable. If it was a variable, I'd have to factor it out as a GCF. But since it's just a constant, I could go ahead, and that's going to change my equation. It's going to make it a little bit easier as 2 cosine squared of x plus cosine of x minus 1 equals 0. We could factor that as 2 cosine of x minus 1 times the cosine of x plus 1 equals 0. Zero product property kicks in. Either 2 cosine of x minus 1 has to be a 0, or the cosine of x plus 1 has to be 0. Okay? Now, to avoid a little motion sickness, we'll just stay on this side. And if we solve this, we subtract 1 off for each side, and we get that cosine of x equals negative 1. Okay? Now, to remind you, this did want us to find solutions between 0 and 2 pi. So cosine is negative in the second quadrant and the third quadrant. And, oops, look at me getting ahead of myself. Not getting ahead of myself, just forgetting myself. Cosine of x equal -1 is a quadrantal angle. Silly me. So that means we either got to be here, 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 or here, which is 1, 0, 0, 1, -1, 0, and 0, -1. Well, the one that gives us the -1 is this right here. So we get x equal to pi. So that's the solution we get from that part of our equation. Then if we come over here to the other part of our equation, we can add 1 to both sides, and we get 2 cosine of x equals 1. Divide each side by 2, and we get that the cosine of x has to equal 1/2. Again, 0 to 2 pi. We have a positive ratio, so it's in quadrant 1 or 4. Cosine is adjacent over hypotenuse, and that happens to be a reference angle of pi over 3. Pi over 3. So measuring from 0, we get this answer, which is pi over 3. And then from 0 to here, we get the answer of 5 pi over 3. So ultimately, if I look at all my possible answers, x equals pi over 3, 5 pi over 3, or pi. And that's that.